Hi, so now we're covering chapter 9. In the previous chapter, we looked at the simple carbohydrates, and now we are going to look at the complex carbohydrates and what they are, their function, and of course, nutrition. So, what are complex carbohydrates? So we are going to term these polysaccharides. So previously we talked about saccharides or sugars or any carbohydrates really, and we had the monosaccharides and disaccharides. So polysaccharides, of course, means that it's going to be composed of many sugar units rather than just one or two. The complex carbohydrates can be classified as macromolecules, and these are any large molecule that contains hundreds or thousands of atoms. And so that within that classification, you of course have the complex carbohydrates. You also have proteins, lipids, and nucleic acids are all considered macromolecules. So we can further classify these complex carbohydrates into several different types. The first type is going to be the starches. So the starches, um, they are chains of alpha D glucose molecules. So if you remember that D glucose is the natural form of glucose, and that can be alpha or beta, and alpha is digestible and beta is not. Okay, so the starches are alpha, so they're the digestible complex carbohydrates, and they are further classified into two main types of starches, and those are amylose. And amylose forms linear chains of glucose. Okay, so this polysaccharide is multiple glucose molecules in a chain together, and it's nothing but glucose. Then amylopectin is a branched chain of glucose. So it is also only composed of glucose, but instead of just being one long chain, it's going to be branched out. Okay. And they have a little bit different functionality, which we will get to in a little bit. Okay, so the sources of starches. We find starches in all of our grains, so wheat, oats, barley, etc. Any seeds have starch as a big component of it. And of course, root vegetables are potatoes, carrots, tapioca is a root vegetable, arrowroot, and specifically, well, not so much carrots, but potatoes, tapioca, arrowroot. Those are actually common, starch ingredients. You find potato starch at the grocery store, tapioca starch, or arrowroot starch. Also, are legumes, so beans, peas, etc., are all high sources of starch. And finally, some squashes, not all squash, so like zucchini is not a good source of starch, for example, but some starches or some squashes are high in starch, and those include acorn squash, butternut squash, and of course pumpkin. So usually when we are just saying starch and when we are finding these sources of starch naturally, the starch is going to be a mixture of the two starch forms. It's going to be a mixture of amylopectin, which is usually between 65 and 85%, and the amylose form of starch, which is typically going to be in smaller quantities. But the ratio that we find that is going to determine what kind of properties that particular starch has, because the two do behave differently as far as functionality in foods. Okay. There's also in some some sources of starch are classified as waxy starches. So for example, an example of properties. And so like they seem more waxy, they're shinier, etc. And these starches are going to be composed of mostly amylopectin. Okay, so this figure here is actually an example of a starch granule. Um, and so when the starch forms, it is a mixture of the amylose and amylopectin, and it will form a granule. And it's just like these two groups of amylose and amylopectin interacting with each other to form kind of like a ball, um, and you'll find it looking like that. Okay, so second type of complex carbohydrates is cellulose, okay? And of course, those are the beta D glucose molecules. That should be glucose, not glucoses. And so beta D glucose is the indigestible form of glucose. And this form of complex carbohydrates, the cellulose, forms the rigid structure of plants, and it's fiber. It is not digestible by humans. And so what you'll actually see here as far as structure here, you have the chain of glucose molecules that are the beta D-glucose chains, and there's hydrogen bonding that is across the chains. So you have a chain here, but in between chains, there is hydrogen bonding. So that you have this hydrogen here bonding with this oxygen here, okay, for example. And that helps even further form that rigid structure of the cellulose. Then the third main type of carbohydrates, we kind of group them together, and I'll go over each one separately, but gums and pectins. So the first one is gums, and these are soluble in water and extracted from plants, and they are used to thicken and stabilize mixtures for food. They also help trap color and flavor, and you'll often find these gums in salad dressing, sauces, ice cream, yogurt, gummy candies, etc. Now, the gums are also fiber. So they have the beta D glucose in them, um, but they are soluble fiber. And so there's two types of fiber. There's soluble and insoluble. Cellulose is insoluble. The gums and pectins are both soluble fiber. So they do dissolve in water, but they are not digestible by our bodies. So then pectins are found in plant cells, and they're made of chemical derivatives of sugars called sugar acids. And of course, they naturally occur in fruits, and they produce a strong, stable gel. So also, in the presence of sugar, these molecules will dehydrate. They'll give up their water to the sugar. And in addition, when you add acid, that causes hydrogen bonding and a thickened structure. And that is how these molecules produce the strong gel that we find in jams, jellies, and marmalades. And we'll go into that in a little bit more detail in a few slides. So now let's talk about the functions of the complex carbohydrates in foods. So first function is to provide structure. And all complex carbohydrates stabilize food products by keeping the ingredients evenly distributed throughout the mixture. That's just a way that they stabilize the food products. But there's three main functions that we're going to go over in more detail. So providing structure, starch provides bulk and structure, all right? And when starch is heated, it thickens up. When it's cooled, it then forms a gel. And so in baked goods in particular, this, along with the protein that we talked about last week, the starch forms this gel. Even in the baked good, you can consider it a gel if it is heated and then cools down and it hardens. There's also other foreign products. So this right here is cornflakes. So screenshots from a video of cornflakes. And the way that they produce cornflakes is they have actual corn and they soak it in hot water for a while and until it becomes soft. And then they grind it to mush. Okay, so this is what this is. It's just like a corn mush here. And they've taken out the like exterior of the corn kernel that is more fibrous and cellulose. And all you're left with is this corn mush. And then they actually send it through a machine that forms it into the cornflake shape. And once it's in that shape, they just dry it really quickly. And so this cornflake shape, it's just held together by the bonding of the starch molecules, because this doesn't have a lot of protein in it or anything else that's going to provide that structure. And so that's kind of just what cornflakes are. It's like mush formed into flakes and then dried. Okay, as far as cellulose, the structure, it's mostly gonna be like in the fruits or vegetables themselves. It provides that structure. As far as like a food ingredient, it typically doesn't provide a lot of structure, and that's partly because it doesn't interact well with other foods or with other chemical compounds. Okay, so the second function is binding. So the first function is structure, the second function is binding, and binding is simply holding two substances together. So examples of complex carbohydrates and binding is batters, right? We have a piece of chicken and we are binding, the batter is going to bind to the chicken and form this nice crunchy exterior layer after we cook it. Okay. So the starch molecules are actually physically able to bind to other chemical compounds, such as the proteins in chicken. Now, amylose is better than amylopectin at this binding function. So it's important when you're choosing what source of complex carbohydrates, what source of starch that you are using for your batter, to choose something that is, if you choose something that's higher than amylose versus amylopectin in that ratio, you'll have better binding of that starch. It also helps to let that batter sit and have time to bind to the protein before you fry it, and so that it will stay on the chicken or whatever you've battered. Because it's a chemical reaction, it needs time to happen. Another example of a complex carbohydrate and binding is carrageenan. So carrageenan is actually a carbohydrate that is extracted from red seaweed. So there's a picture of red seaweed here. And it's really good at binding lots of things. It's good at binding water. One of the things that you'll see it most commonly used in is actually chocolate milk, because it's good at kind of being an interface between the cocoa and the milk. Because if you've ever just like dumped cocoa into a liquid, milk or water, it doesn't really mix well, right? And even if it does, then it'll start to like settle at the bottom. And so what carrageenan does is, if you've seen chocolate milk in the stores, it's not settled at the bottom and it's all nice and creamy and smooth. And that is because of the carrageenan has helped bind that cocoa to the milk. It's also sometimes used in processed meats. It's great at binding everything. Water, protein, fat, carbohydrates, everything. And so in some processed meats, you can add carrageenan and it helps it hold water, be more juicy, just kind of keep all of those things together. And so you don't have like water coming out, whether it's during cooking through evaporation, or just if you had something just sitting and it's exudate onto your plate or in your storage container before you cook it or whatever. So carrageenan is good binder. Then xanthan gum, also a good binder. You'll see these used a lot in gluten-free food. So if you like get a gluten-free cake mix from the store, if you look at those ingredients, there's usually going to be some kind of gum in there. And that's because in regular gluten foods, gluten itself provides binding, and really helps with the structure of those foods. And so you need to have something in there to replace that, to get the same kind of binding, so your cookies, for example, stay together and don't crumble. And that is something that the gums provide. Third function of complex carbohydrates is thickening. So again, we'll start with starch. And so undamaged starch is fairly insoluble in water. So you add cornstarch to water and you might get it to mix, but then you let it sit and it settles down to the bottom, right? So it's not very soluble in water. But if you heat the water, or heat the solution, then it breaks the intermolecular bonds that are between the amylose and the amylopectin, right, of the starch granule, and exposes the polar structure. So remember that these starches are composed of glucose, and glucose has lots of hydroxyl groups, which are polar. So if we break the bonds in between them, the hydrogen bonds between the amylose and amylopectin molecules, now those hydroxyl groups are exposed. They're not bonding with each other again anymore. They're exposed, and water can come in and now bind to those hydroxyl groups. And so the water gets into those crevices as those bonds are broken with heat, and the starch granules start to swell in a process that is called gelatinization. And with that, the water or the solution becomes thicker. You are swelling those starch granules and water is binding. You're having less water that is loose in solution and more that is bound to the starch. And all of that results in a thickening effect in your solution. Okay, and so the temperature at which that maximum swelling occurs is called the gelatinization point. Okay, so this figure here, you have the starch granule heating, and water is able to get in between the molecules of the starch granule, and um, that is gelatinized starch. Um, Now, past that temperature, so this is our gelatinization point. Past that temperature, you actually can have a reduction in the thickening. And so it's kind of important to know what that temperature is, because you go past that, you start to lose some of that thickening functionality that you've gained. And you can really lose it by a certain temperature, because you can actually completely disrupt the starch, and then end up with back more liquidy solution rather than a thickened, more viscous solution. So other factors that reduce that gelatinization. So higher prolonged heat, so that's what I was just saying, is too high heat. We get temperatures too high, they cause hydrolyzation. We've talked before about heat hydrolyzes sugars, right? So that you add water and break apart the sugar, hydrolysis. And so too high heat, those starch molecules begin to break apart, and without them being held together, there isn't anything to trap all of that water. And so you lose some of that thickening. Another example of something that can reduce the gelatinization are salt and sugar. And that's because salt and sugar are also polar. They can potentially compete for the water. Salt, of course, separates into its ions in water, but those ions are attracted to the hydrogen and oxygen in water too. Now, the salt isn't typically too much of a factor at lower concentrations, but the sugar can be. So here is, I grabbed a couple charts from some studies. So this figure here is looking at different types of starch in either a neutral, so just distilled water system, or a system where they've added both sugar and acid, because also acid can affect reduced gelatinization too. So we have the TS is tapioca starch, RS is rice starch, and then the WTS and WRS are the waxy versions of those that, remember, have more amylopectin in them. Okay, so with the tapioca starch, there's really no effect of salt and sugar. Okay, it's pretty immune to that, whether it's the waxy or the regular starch. But the rice starch, if you put that rice starch in a sugar acid system, it now has much lower swelling power. Okay. Another interesting thing to note is the waxy version, the version with more amylopectin, has greater swelling power overall compared to the regular starches. And that makes a little bit of sense, because amylopectin is the one that has all of those branches, and so there are more crevices for the water to get into once you've broken intermolecular bonds with heating. Then this second figure is corn starch with different levels of salt that have been added. Okay, so the NS is normal starch, the WS is waxy starch, and the HS is a high amylose starch. Right, so waxy starch would be a high amylopectin starch, and high amylose starch here for the HS. Okay, so The waxy starch, if we're just looking at this, has the greatest swelling power, which kind of corresponds to what you saw in this other study. The normal starch next, and the starch with just amylose has almost no swelling power, right? Then, uh, and then adding salt, right? So let's look at this waxy starch because it's the easiest to see, and these are going to follow the same pattern, but they're just closer together. So the salt with the one with 2% salt is the lowest swelling power, and the one with 0% salt is the highest swelling power in that. So you can see as you add more salt, you reduce the swelling power. In addition, amylopectin, the waxy starches, are going to have greater swelling power compared to starches that are a greater proportion of amylose. And that's because the amylopectin has lots of branches, so there's more crevices for the water to go into. Continuing with thickening, now let's talk about pectin. But just kind of go into pectin a little bit more. So like we've said before, it's used to thicken jams and jellies. And pectin is primarily going to be found in the peels, the seeds, and the cores of fruit and some vegetables. You're going to find more amylopectin in unripe fruits. As fruit ripens, pectin is converted into pectic acid, which makes the fruit softer as well as more acidic. Okay. So fruits that are high in pectin include citrus, primarily in the peel, and the pith, which is the white part that's in the core of the citrus. Also, pectin is high in apples. And so, hold on a second. Okay, so it's high in apples, primarily, again, in the peel and in the core, like the part that's just less edible in the core of the apple. You'll find more pectin. And commercial pectin, so when you buy pectin that is sold in stores so that you can make jams and jellies, it's actually made from citrus peels and as well as sometimes apple pomace, which is the leftovers from juice production. As far as apples, you'll find more pectin in apples that are underripe, right? Or tart varieties of apples. So, for example, the book mentions crab apples as a source of pectin. That is an apple variety, and it is very tart. And so they are a great source of pectin because they fall under that. Also, blackberries, as long as they're not too ripe, have high pectin. Cranberries are a good source also. Also, some grape varieties have higher pectin, specifically Concord grapes, which is what is used to make like grape jelly and jam for the most part, but not all grapes. Carrots, unripe bananas, apricots, peas, sweet potatoes, those are some other alternative sources of pectin. The reason it's good to know what fruits are high in pectin is because that kind of tells you if you are making a jam or jelly, if you can make it with just the fruit, if it has a high enough pectin to have enough pectin itself to create that jam or jelly, or if you're going to have to buy some commercial fruit pectin to add to your solution to make sure that it gels up. So generally, the formula for using pectin, and this would be good to generally know, I would say, is that you have a 1% pectin, so it's not a whole lot of pectin that you need. And then you add sugar, and you add your crushed fruit or juice. The key thing here is that this is a source of water, because you do need water to produce this gel that the pectin's going to form, and acid. You want to get the pH down to 2 to 3.5. Now, sometimes you don't need to add acid. If your crushed fruit or juice is acidic enough, you won't need to add another source of acid. But those are the key ingredients. You need pectin, sugar, water, and acid. 4 things: pectin, water, sugar, acid. Calcium can be used in place of sugar to form gel, and this is just kind of important to know if you're making a sugar-free version of a jelly. It's not going to work if you haven't put something in there to replace the sugar that will interact with the pectin, and so there's calcium ingredients that can be used to help form that gel. Okay, so continuing on with thickening, just real quick, alginates, which are a form of gum, carbohydrate gum, also used to thicken dressings and puddings. Xanthan gum can be used to thicken puddings too. So like Velveeta has alginates, and this is a vegan cream cheese that has xanthan gum in it. Now, when I talk about gums, this is absolutely not the same kind of gum that like chewing gum. It has the same word, but it's not the same kind of thing. It's not chewing gum that is being added into products. Okay. So now moving on, we're going to talk about the types of starch and liquid mixtures. And so the book kind of lists them. The first is slurries, and the key thing I want you to understand about slurries is they are uncooked mixtures. Okay, so any mixture of water and starch that has not been cooked is a slurry. Okay. Now, commercially, these slurries are really just the preparation before processing into starch products. So, like, they isolate the starch, they form it into a slurry, and then they're going to use that slurry to form other starch products that they're going to sell, whether it's a crystallized starch or a starch that has been formed into a gel already, or they are modifying the starch, which we'll talk about modified starches next week. But essentially that slurry is just a step in the commercial process before it's turned into something else that is more sellable, whether it's just refined a little bit or converted into something else. Okay. Now at home, we use slurries for making starch mixtures when we're cooking. And I think we get to this part next week in the book, but this is also known as a cold water paste. So in the book, it's referring to what's really a slurry. As far as it being an uncooked mixture, it falls under this definition, but we call it a cold water paste. And you'll make a paste or slurry, small slurry of your starch before you add it into your solution, and we'll talk about why that is next week. So slurries, uncooked. Next step down is sols. So sols is kind of just like the word sols is just like a smaller version of the word solutions. Okay. And these are thickened, pourable liquids. So this is a batter. This is white sauce. This is gravy. Anything that has some form of starch added to it. Now, when I'm saying starch, it does not have to necessarily be I added cornstarch. White flour is heavily starch, right? There's other proteins in it too, but it's not pure starch, but it's heavy in starch. It has lots of complex carbohydrates in it, okay? And so you're making a batter. Yes, I'm using flour to make that batter. That is part of this, okay? It's heavy in starch. It falls under these definitions. The next level of liquid mixtures of starch is a paste, all right? So as we're going through this, we're just getting thicker, okay? Sols are batters, or pourable liquids. Pastes are not. They don't have much flow. They're much more thick. Um, so I tried to look for commercial examples of pastes and really couldn't find a whole lot. The most common thing I found, just like doing an internet search, as far as a paste that you can buy that is made of starch, would be they sell starch pastes that are used for book binding and book archival. So not really food science related, but it is made out of starch. They often use tapioca starch for it. But commercially, a food manufacturer might buy a paste that has been pre-made so that they can blend it directly into their mixture. That would be an example. Then the final level of starch liquid mixtures is a gel. And so these are mixtures that are rigid. Now, in the book, it talks about junctions. I want you to completely disregard that term in the book. Don't use it. And they don't really define it very well. That it makes it sound like the hydrogens are bonding together, and that's not possible. For hydrogens intermolecularly that are already bonded to something else to bond to each other, it's not possible. Instead, what's actually happening when it's talking about these junctions is that it's just the same type of hydrogen bond that we've been talking about, where we get hydrogens and oxygens forming hydrogen bonds across hydroxyl groups of different molecules, okay? Starches that are predominantly amylose molecules form more rigid gels. I kind of talked about how the ones that are have more amylopectin will uh, will hold on a second. The ones that are more amylopectin will swell more, but the ones that have more amylose will be more rigid. Okay, and so why is this? The amylose molecules are straight chains. This is my little art here that I did myself. Okay, so they kind of lay against each other and form lots of hydrogen bonds. Okay, and the more hydrogen bonds that we can form, the stronger that structure is going to be. You compare that to amylopectin. So these are two amylopectin molecules, okay? They're just all twisty, okay? And just my bad art. And you can see that there's a lot less spots that can bond compared to how big that molecule actually is, okay? The last picture here is a mixture, okay? So we have amylose and amylopectin, which is a little bit more realistic. We're not going to have just one or just the other. But you can see, even with the mixture, if we have more amylose, we get more bonds. So the key thing here is that the more amylopectin is part of the starch, yes, you get more swelling, but it's not going to bond together and be as rigid. And so the weaker that gelation is going to be. Okay, so more amylose equals a stronger, more rigid gel. More amylopectin is just more swelling in the gel. Now, continuing along those veins, so with the gelation, the gelation is actually going to happen mostly during cooling. So with the heat, you get the hydrolysis, and the hydrogen bonds are unbonded, and water can get in. But during cooling is where these hydrogen bonds rebond, all right, wherever the water hasn't gotten in there. The hydrogen bonds across the molecules of amylose or amylopectin rebond, and the starch granules are trying to just reform that structure that they had before cooking. Okay, this is called retrogradation. Okay, the forming of a gel during cooling and standing. Okay, retrogradation is reversible. So if you reheat the starch, then you're going to break those hydrogen bonds again and reverse that process. So retrogradation, it's good when it forms the appropriate gel, because that's the goal of a lot of times when we're using starches, is to form that gel. It is bad when the gelation continues to the point that cracks form. So your gel is too rigid. And when syneresis occurs, which is when water is squeezed out from between two substances. So as that gel becomes more rigid and the bonds bring everything together, it actually just pushes water out of it. And you end up with just like a thin water layer around your gel. So example, or examples. This one here. So this is, you have dough, you have gelatinization as you're baking it, you have fresh bread, and over time you have retrogradation. So you have bonds beginning to form, and it pushes the water out a little bit, and that water evaporates and you get staling. Now, you actually start to get some retrogradation even here as soon as it stops cooking. And some of that is good. So think about a cake. And cake is way too sticky when it first comes out of the oven. If you try to cut it hot, you're going to get sticky crumbs everywhere. But as you cool it, retrogradation occurs, and you are forming an appropriate gel, and then you can cut it and it stays together better. Okay. A more obvious example is a gravy. It is thinner as you're cooking it, but as it cools, it will thicken up. Now, the key thing here is understanding that retrogradation will happen, and using it to your benefit, knowing when to stop thickening your product, understanding when that it will happen and when to stop cooking as far as your product thickening. So if you are serving your product hot, like a gravy, for example, you want to basically cook it to the consistency that you want it to be at when it's serving, right? But if you're making something that will be cool by the time you serve it, like a cool sauce, like a cool sugary sauce that you're gonna drizzle over a cake or something, then you want to stop cooking when it's at a point that it's not quite as thick as what it's going to be when you serve it, knowing that as you cool it, it's going to thicken up. Okay. Now syneresis, generally is never, I can't think of any example where it's a good thing, but it's kind of a normal thing for a lot of products. So an example is the water at the top of the ketchup or the mustard, if you don't shake it first, right? Or other examples would be yogurt also gets a layer of water at the top, or sour cream. Um, Homemade jelly is more prone to syneresis because it has less things to hold that water. And so you might get just like a layer of water at the top of that jelly during storage. Okay. Generally, the more stable a gel is, the less syneresis that it has. So acids reduce retrogradation. So if we're thinking about, and the book gives this example, and I'll just kind of repeating it, but if you think about a lemon pie, there has to be acid in it because you have to have that lemon flavor. But you need it to set because this is, there's not a lot holding all of this together, right? Except for the complex carbohydrates. And so the key thing to know with that is that recipes that are going to have acid in them will need more starch to make up for the fact that gelation, because retrogradation can be a good thing, right? That it causes the gelation of this pie. And so that gelation is going to be affected by the acid. And so you're going to want to add some extra starch to make up for that. Also, things that you can do to help with that is with like a lemon pie, you add that acid very last and cool it quickly so that it has less interaction and time to affect it. Okay, so some properties of starch. The first one is viscosity. So viscosity is a pretty key term that you need to understand what viscosity is. Because easy, even in my head sometimes, to get it flipped around and you think it means the opposite of what it means. So viscosity is the resistance of a mixture to the flow, and it's a measure of starch's thickening ability. So, a viscous substance is a thick substance. Okay. So if a substance is less viscous, it is more thin, more runny. Okay. A viscous substance is a thick, slow flowing liquid. Okay. One way, or sorry, so going back to the starch solutions that we talked about a few slides ago. So in order of viscosity, gels are more viscous than pastes, which are more viscous than salts. Okay. So some ways that we measure viscosity. So one way to measure the viscosity is the line spreadsheet. We'll be doing this in class next in 2 weeks. It's the second week that we do labs for this chapter. So this is a line spreadsheet. You have a cylinder in the middle of several printed rings, and you'll fill the cylinder with a specified volume, and then you lift the cylinder up and allow the volume of liquid to spread across the page. And so after a specified time, you will read how far, like what's the radius of what it got to at 4 different points, and average those readings. So a lower viscosity liquid will travel further over time, right? and then a higher viscosity liquid will remain close to where it was originally poured within that cylinder. Okay. So another example of something that you could use to measure viscosity. So this little thing here, it's a cup, but it has a hole in the bottom. And so you would lower it down into the liquid and then and let it fill up all the way, and then raise it up, and you start timing it, and how long does it take for the liquid to completely empty from this cup from the hole that's in the bottom. And that would be another measure of viscosity. And there are other tools to measure viscosity too, but those are just a couple examples. So in general, if you have a solution that has larger molecules, it's going to be more viscous because larger molecules are they're harder for them to move, right? If you have a solution that has lots of linear molecules, so for example, more amylose, it's going to be more viscous than a solution with lots of branched molecules. And that's because, okay, if you have linear, it's harder for the linear to tumble over themselves versus a branch molecule, which is more spherical. It's easier for it to flow. Okay. So that explains that. And then finally, if you have a solution that has more charged molecules, it's going to be more viscous than one with uncharged molecules. And that is just because of charged molecules are going to have are going to have, be attracted to each other and kind of holding each other together. And so there's more resistance in that situation because they are attracted to other molecules around them versus a solution that is all uncharged molecules. Okay. Okay. Next property of starches that you want to consider when you are choosing starches is stability. So stability is the ability of a thickened mixture to remain constant over time and temperature changes. And so how stable a gel or paste or sol does this starch form? If I freeze my salt and then thaw it, if I refrigerate it and then reheat it, is it going to look and taste the same as when it was prepared? And that is going to vary across different starches. The easiest example is a flour mixture. Flour mixtures are more stable than cornstarch mixtures. So you refrigerate a gravy and reheat it. It's generally going to be pretty close to the same gravy once you've reheated it versus a cornstarch mixture is not. You're more likely to have had syneresis that's gone on and while it was refrigerated and potentially end up with like some lumps and things when you reheat. Okay. The third property is opacity or opacity. Okay. And this is a measure of how much an object blocks light. So if something is opaque, it blocks light. And then the opposite of opacity would be translucency, how much, and that would be something that lets a lot of light through, right? So if you're measuring opacity, how much light's being blocked. If you're measuring translucency, you're measuring how much light can pass through. Okay, so generally wheat flour produces opaque sauces, and corn are starch flours that are more pure starch, like cornstarch, potato starch, arrowroot. Those produce more translucent sauces. And so this picture is from the book, but it was a really good example. It's darker. It happens to be darker, but it is also more translucent. Okay, a fourth property is texture. And that's just recognizing that different sources of starch will have different mouth feels. Some are much more smooth than others. And I believe the book gives this example. So cornmeal, if you've ever, I mean, I'm sure most of you have touched or even had cornmeal in your mouth if you've like tried to lick the bowl after your mom or you made cornbread. It has a gritty texture, and that doesn't go away with being mixed in a liquid solution. And so whatever starch solution you make of that, it's going to have that texture versus if you have whole wheat flour, that is going to have more texture than white flour. And then, I don't have this on the slide, but then if you have just a cornstarch, that is going to have a smoother texture than what the whole wheat flour has. So if you're going for a certain smoothness or roughness to your texture, you want to choose your source of starch accordingly. So that is where we are going to stop. Um, and so then next week we'll get into modified starches on page 252 and cover some more about how we thicken sauces with starch, and then get into nutrition with complex carbohydrates next week.